Let's evaluate this double integral that we see on the screen. So this is the double integral over the region R, 6xy divided by 1 plus x squared dA, where our region R is xy such that x goes from -4 to 4 and y goes from 0 to 1. So basically what we are doing here is we have our coordinate system, and if we have our triangular region, I'm just going to randomly draw a region here, so some triangular region. Basically this is that was the same problem, it just reappeared from previous copying. Anyway, basically if we have this triangular region and we're integrating over it surface like this. This is our surface and this is our region we're integrating over, and basically what we have, and let me draw that a little higher. Draw that surface a little higher so I can, yeah, that's better. What I'm doing is I'm integrating over this specific region. And what that effectively does is creates this sort of space in between. And this space we can find the volume of. We can find the volume of the space in between. That is essentially what we are doing. That is the goal when we think about double integrals. So let's do that with this example here. Let's set up a double integral. Okay, let's do that. So double integral over the region R, 6xy 1 plus x squared dA is what we have. We can take this and we can set the bounds. So let's set the bounds. What I'm going to do is I'm going to just set the x going from -4 to 4 first, and then I'll do the y. Now for this specific problem, the way it is, it's kind of interesting. So dy dx, it's kind of interesting because you can split it up. What you can do is take this function, this multivariable function f of xy, which is 6xy plus over 1 plus x squared, and you can write this as 6x over 1 plus x squared times y. That's what you can do. You can write it like this. The benefit with writing it like this is that you can split up the double integral, and you can do this only when you have a case like this, and when you have a region like a rectangular region that's not like a type 1 type 2 region. So that means that we don't have like an expression here, we just have a number. So what I can do with this integral is just set this up as -4 to 4, and then this is x, so this is 6x over 1 plus x squared dx, and then times 0 to 1, just y dy. That's equivalent to that. You might not know this kind of trick, but it's kind of intuitive and obvious. And once you learn it, maybe it's not that intuitive, but once you learn it, it's definitely pretty nice to use for some problems to easy up the integration. So if I just go ahead and set my u, in this case, to equal to 1 plus 2x, so that I can set my du equal to 1 plus x squared, not 2x, 1 plus x squared, du equals to 2x dx. That is, here we can split this up as 3 times 2. 2x dx is du, and then divide that by u. And we still have our 3. That's not disappearing. And then this is going from not -4 to 4 anymore, but 1 plus -4 squared, which is going to be 1 plus 16. 17. Same thing here actually. 1 plus 4 squared is 16. 16 plus 1 is 17. That's interesting. This is interesting. Let's ignore that for now. And really, actually, we don't have to ignore it, because if we compute this, it will actually get our answer. But let me actually just move on and just not worry about the fact that they have the same, the bounds are equal. What this is going to become is y squared over 2, 1, 0, which just becomes 1/2. It's just 1/2. Again, we're integrating, so it's y squared over 2, and then 1, 0, and what happens is 1 squared over 2 minus 0 squared over 2, just for those who need a little more steps, it's 1/2. Okay, but does this matter? No, because when we have an integral where the bounds are equal, the bounds of integration are equal to one another, this ends up becoming 0, and I'll tell you why. If you don't remember. Think about your xy, and forget that we're in 3D, so the good old days where we weren't in 3D. Oh, sorry, what am I doing? X, Y. So if we have our function like this, what we did when we integrated from x equals a to x equals b, we found the area under the curve. That's what we did. That's what we first learned integration. That's what we thought about when we first learned how to integrate. Quite simple, not too difficult. However, if a equals b, so we have our same function, but if a and b are the same thing, they're the exact same thing, so a and b are the same thing, the same value, so that is a equals b, then notice that we have no area there. There is 0 area. So since there is 0 area, the integral from a to b okay, let's start with this case, from a to b, f of x, say if this curve is f of x, dx is just going to be some number. Okay, some number. It's going to be some value. So some value, whatever it is. Okay, I'm just going to say dot dot dot. But this value from a to b, given that a equals b of f of x dx is equal to 0, and I should maybe instead of doing this, I'll just say is not equal to 0, and this is equal to 0 because of the fact that there is no area in between. So that's why this is 0, which gives you that this entire thing is 0, so this is 0, and that is the value of the double integral. I think this video is unnecessarily long, but I've made some interesting drawings, so hopefully you enjoyed it.